Hello, welcome. I've been doing quite a bit of reading on geometric algebra, and I asked myself the question: if there's a geometric algebra, is there a geometric calculus? Oh yeah, oh yeah. Then I started snooping around and saying, I've been out of school a really long time. Is it just me being old, or is this stuff being taught? It's not, and it's gained like a cult status. This stuff. It has websites, it has forums, it even has a LinkedIn, the forum. There's YouTube channels devoted to this. There's books now. And I just asked myself this question, well, if it's so great, should it be taught in schools? And if it's not, why is it not? So I just asked the Google AI, and it had us some pretty good the points. Arguments for teaching geometric algebra. Now it had lots of words to go with each one of these bullets, but it's too boring to read. Unified mathematical language. They claim that it unifies many different types of algebra, matrix algebra and vector algebra, etc. And it gives a more enhanced geometric intuition to students. Now, I actually one part of this I can believe, and and I'll talk about that in a minute. And it says it's a powerful tool for physics. Now, I have not seen this yet. I have not found anywhere, I don't have any books on this. I've not found anywhere on the internet that this gives a more powerful tool to physics than what we already use. I don't know. I may be missing something. Arguments against teaching geometric algebra. Curriculum constraints. Already, they're saying it's so crowded. How in the hell can we put something else in there? And most math teachers don't have any background in it, and it's complexity, and it is gets a little bit abstract very quickly. And they also claim, we haven't established the curriculums of mathematics that's been going on for a long time, and it seems to be working. So would we really want to monkey with that? So here was their conclusion: geometric algebra holds significant potential as a powerful and unifying mathematical tool. However, its widespread adoption in schools should require careful consideration of curriculum constraints, teacher training, and potential for increased complexity. So, I haven't been studying this very long, but I've come to a few conclusions on my own. I think the wedge the product would be useful for students to learn. It seems to me more intuitive than the cross the product. If you're trying to teach the cross the product in a two-dimensional on a you're teaching two-dimensional vector, the multiplication, inner product, outer the product. The cross the product, it really doesn't make much sense. Actually, you can't even do it in two dimension. If you do, it doesn't make much sense. The wedge, the product is rather intuitive. It gives you a bivector, and that bivector uh, has a direction and it has a magnitude. It's either positive or negative, and it forms a the parallelogram, and that area of that parallelogram is the value, the magnitude of the wedge, the product. So I think it should be taught. I really think this is a very handy little tool. Now, the flagship of geometric algebra is the geometric product, and you won't get very far in studying it and using it unless you come to grips with this. Now, I'm not a teacher. I've never been a teacher, but I've been a student for a really long time. So, how in the heck would you teach this to a student? The product of vector A with vector B is the inner product, the product, plus the outer product, the wedge, the product. What? How do you draw that? What is this thing? I've already seen the use of it, how it can be used, but just geometrically, to me, this makes no sense at all. So I said, okay, well, I'm going to look a little bit at the calculus, okay? Well, the geometric calculus is also based on the product, which they call the gradient. Now, if you think this one gives you goosebumps, what do you look at this one? They're saying as an example, the product of the Dell operator with a F is the inner product plus the product, where f can be any combination of scalars, vectors, or multivectors. Now, wow. When you take the gradient, the divergence or the curl of vector the fields or scalar fields, whatever you're doing, there's a geometric interpretation to that. You can actually draw it on paper, right? You know what that means. Well, what does this mean? On how would you draw this? How would you graph this? I have no idea. So I think this is one of the things that would be holding this back in school is you have to do this in order to progress in that subject, but what the hell is it? I think it's incredibly wacky. Anyway, I'm interested in what you think. Let me know. Thank you.